electrons are paired. So millions of molecules which we make, billions of molecules basically, the electrons are paired up. Okay, and that's the reason the molecules are actually, mostly the molecules of this type are stable. But today, which we'll be describing, are a very different class of molecules. Here, the molecules have unpaired electron. One electron is unpaired. So that means one electron is taken out of the molecule. Either taken out or given. If you take out, then also there will be one electron. If you give also, then also there will be one electron. So these are the classes of molecules which we will discuss. And when I discuss about the applications can be massive. Why massive? It can be for material science, it can be applied in magnetism, organic magnetism. It can be highly conductive because you have a single electron in that unpaired electron in the valence shell. These can be used for sensors, these can be used as antioxidants, many different types of applications. But the major problem with these type of molecules, you can easily understand, is the stability. Because one electron has been taken out. Now this molecule is free to react with the environment. And what's the environment there? Environment has oxygen, which is reactive, and also light, as well as your solvent or your moisture. All these can react with these organic radicals. So this is the problem basically in this area. And I started this reaction by accident. When I started my career in School of Physical Sciences, it started as an accident, but I loved this chemistry from our textbook chemistry. We have to read in chemistry this as a chapter. From bachelor's to master's, we have this chapter of organic radicals. Many people like it, many people don't like it. Because many people don't like it because these are transient formed materials. Transiently formed materials. Nobody likes to have a transiently formed materials. But then these species formed as an accident in our lab, and one of my earlier students said, "Sir, the spectrum which I am getting in UV visible absorption spectroscopy, spectrometer, this is corresponding to a radical. And that radical had some lifetime. That's the reason my student could see it." Right? And then you will be amazed that, and this is, I can't actually explain you, this is a part of a story. Before few days, as you know, there are book vendors, right, who come, most probably also in your institutes, they come to your office and give some books, right? So before few days of this accidental finding of this radical, one vendor had come and give me few books. And one of the book was of a radical, organic radicals, written by a Russian scientist. It's a very thorough book, this much thick, big. And I had no idea that, okay, I just kept it. And this is a connection. I thought that, okay, there must be then a connection that, okay. And that book is still there, I had kept it. And then every chapter I went through, oh, amazing. Okay, so 30 minutes, I made much more slides. I'll give you the basics of it and some of the things which we have done in our lab. But this is really applicable to material science. This is really applicable to biology. If you can stabilize it. Now there are examples, only few, where radicals have been also stabilized in water. There are only very few examples, recently came. So that's a thing, because organic chemists or molecular chemists actually can design by ideas, right? So now ideas are there to stabilize those even in water and under ambient condition. We also started working after we got this accidentally. We also started working to stabilize those. I'll show in the last part of my talk how we have stabilized it. But first, because it's a diverse audience, I'll first tell you about the basics of it. Please, whenever you want to ask, please ask it. Don't feel shy. Okay? So this is about our JNU. As you can see, right? You have already seen all these buildings, right? This is our administration building. This is our library. Please go inside the library. This is a very good library actually. And this is the convention center. This is School of Physical Sciences, right? And this is a view of the Qutub Minar from the School of Physical Sciences terrace. From the terrace of the School of Physical Sciences. Okay, you can go and have some tea in the canteen of School of Physical Sciences and see this Qutub Minar on a nice clear sky day. You can see it very nicely. Okay, so outline is brief history of radicals, homolysis and heterolysis. This is a very important thing to understand. Importance of bond dissociation energy. Because if I am taking out one electron, right, or an atom, I need to understand the energy with which it is there already in the molecule. I have to break certain bond or write one electron out of it. So energy comes into picture there. Then there are types of radicals, molecular orbital picture of some radicals. Don't worry about it, right? I'll give you the simplest understanding. And then stability of radicals and important reactions of radicals, which I may skip, and selectivity of radicals, and maybe a quiz or may not be a quiz. This may not be. Okay. So one of the earliest radicals is this. Okay. This is one of the earliest radicals. Do you know, any one of you, what is this radical? This is, we just had 125 years of this radical. So 1900, this radical was discovered in 1900, and this radical was discovered by Professor Gomberg in Germany. Gomberg, and this is called the Gomberg's radical. What you see here, there is a hydrogen there. There is a hydrogen there, and you can easily understand that hydrogen is taken out, right? When you are taking out the hydrogen, what's happening? One electron goes with the hydrogen and one electron stays over the carbon, right? So there is a carbon-hydrogen bond. Carbon-hydrogen bond has two electrons which are shared. You are breaking homolytically. So one electron is there on the carbon, the other electron is there on the hydrogen. And that's the reason the bond dissociation energy can also be important in certain cases. How it happens, this radical from the diamagnetic species? It happens in presence of silver or zinc in dry benzene. In dry benzene, this will form. If there is a moisture, it will not form. Why? Because in moisture it will again start another reactions of forming hydroxy radicals and all that stuff, right? So that's the reason it has to be a dry benzene or toluene and absolutely pure silver or zinc. You can make this Gomberg's, you can make it in a lab, but then what happened? This type of dimerized species is forming. So you can see that electron which is there on the carbon, right, that can come over, this electron can come over here or here or here, and then this can dimerize, and that is what is happening through the para position, because this is nothing but the spin, electronic spin or the electronic charge of that single electron. That electron can delocalize along this para position or ortho position. Ortho position, it does not form a dimer because of the stericism. Ortho is sterically crowded. So that's a reason from the para position it forms a dimer. Okay? And this was discovered only in 1970, this dimeric structure. So these are the papers, 1900, Jack's paper and a German paper by Gomberg. And this is the book, Stable Radicals, Fundamental and Applied Aspects of Odd Electron. If you are interested, please check out this book. And this is the original paper of Professor Gomberg, Jack's 1900, and there was no software to make the structure and all that stuff, right? So this is, you can see that how the molecules have been written, okay? How the molecules are written. So these are nothing but the single bonds, not the triple bond, okay? So this is something very interesting. You think of 1900, there is no NMR, there is no FTIR, there is no single crystal diffractometer, there is no EPR. How you find it out that this is forming? He was a genius. What he did, he reacted this radical with oxygen, okay, and he get this product, starts forming with oxygen bond, and then he heated that, right, pyrolyzed that under heat and find out the weight of carbon, hydrogen, right, easily. Similarly with iodine, he gets this, right, carbon iodine bond and finds out. So from there he finds out the molecular weight. And then this is how he writes. He made a mistake of writing down this. This is not was the case. This dimer. The dimer which I showed you in the last slide was by a NMR. In only 1970s that structure was found. So he made a mistake here. This dimerized product. This was wrong. Now, while he has discovered this, he writes down a very interesting thing in the last line of the paper. He writes down this. This work will be continued and I wish to reserve the field for myself. Can you imagine? Such a bold statement. I want to reserve this field for myself. In the last line, he has already understood that this molecule is amazing. It's unpaired electrons, so it will be conductive, magnetically active, everything. That's the reason. So you will never see this type of a statement in a paper, right? So confident. Okay, so then after that many radicals have come with some lifetime, right? But many of the radicals, this radical is commercially available nowadays. DPPH, you may have heard about it, right? Diphenyl picryl hydrazine radical. It's commercially available. You can buy it. Very expensive. This radical is also very important. This is also commercially available. Then, as you know, this radical you may know, TCNQ radical anion. This radical is known to form superconductor. This radical forms a superconductor with tetrathiafulvalene, TTF. So this is an acceptor. Once it takes an electron from the TTF, it forms a radical anion. So it forms a donor-acceptor charge transfer superconductors. So there are many radicals which are there nowadays with varied stability. Stability is an issue. And these are the radical cations. This radical was 1879, but no data. No data, nothing. And this is called the Worcester's blue. This is the bipyridinium radical. You know, this is a methyl phylogene species radical. So some of these radicals are there, although it seems these are not very stable radicals. Okay, so how radicals can be important to us? Check out this. This happens in our body. Okay, how vitamin E is extremely useful to remove harmful radicals. So many of the molecules that make up the structure of human tissue are susceptible to homolysis in intense light. I showed you an example of the homolysis in the trityl radical, how it forms a trityl radical. So in intense light, these type of phenomena can happen. Why in intense light? Because intense light is a source of energy. It can excite your body. And the body makes use of sophisticated chemistry to protect itself from the action of reactive radical products. This is what it exactly does when you take this, nowadays the sunscreen, right? It makes there is a zinc and zinc oxide and all. You make a protective layer over your skin, right? But our skin can take care itself also, right? If it is not, then we require this. So vitamin E plays an important role in the taming of these radicals. Taming of these radicals, abstraction of the hydrogen from the phenoxyl hydroxyl group produces a relatively stable radical that does not further damage. Let us see the chemistry out of it. So this is our vitamin E, right? And you see what's the important there? In the vitamin E there is a OH group, and you can easily imagine that this OH is important, right? So this is what it happens. So once there is a dangerous and reactive radical which is forming in your skin, it automatically will form a more stable radical. Why a more stable radical will form? So this is the part of the vitamin E. Why a more stable radical will form? Because this radical can delocalize. It can delocalize. And at this position there is an electron deficient oxygen. Oxygen is electron deficient, so it can pull electrons. right? So this electron can actually get delocalized over the structure, and that's the reason our body is actually protected when our skin is actually protected. So this is the mechanism how it happens. If a radical is formed, then this radical is quenched. The radical is getting quenched into an alcoholic species, which is stable, which is benign. There is no problem with this. And the radical which is forming is having a certain lifetime, which will not quickly react into other species. That's the beauty of it. So now let us go directly to the homolysis versus heterolysis. This is, you know this reaction very well. HCl does not form H plus Cl minus in gas phase, as you know. HCl does not form in gas phase, but in aqueous phase it does, right? That's the reason we see some conductivity, right? So when bonds break, so this is what it happens. HCl, when you are heating at 200 degrees centigrade, so at 200 degrees centigrade when you are heating HCl, then you are giving energy. At that energy, you can break the HCl bond and make H dot and Cl dot. So that 200 degrees centigrade is required, which is commensurate with the bond energy of hydrogen and chloro bond. Okay. So this is where your homolysis of the HCl bond can happen with a residual product of H dot and Cl dot. This one, you see the free energy is around 1350 kilojoules per mole. That's the reason you never get this reaction done. 1347 kilojoules per mole. If you remember, in our nature, the strongest bond is of which molecule? The strongest bond formed is nitrogen. Nitrogen has the strongest bond, around 950 kilojoules per mole. This requires much higher energy. Nitrogen is inert. We are absolutely so lucky, right, that nitrogen is inert. 950 kilojoules per mole, and here it's a 1347. Now you will see what happens. As you know, HCl, HBr, HI, the bond dissociation energy comes down, right? You see here, it has come down to 431 kilojoules per mole, and that 431 kilojoules per mole can be attained at 200 degrees centigrade. You can break this HCl into H dot, Cl dot. So then, is there any significance of bond dissociation energy with radical formation? How can we reduce the bond dissociation energy? It's very simple. I gave you the answer, right? You change the size. HF will be much more difficult. HF, HCl 431, and now if you go to HBr and HI, there's a size difference. The bonding is weak. You can create a H dot and I dot at a much lower temperature now, right? With a much lower energy of light also, right? H nu, lower energy of light. So that's what it happens. So now you see the bond energy. Water, 498 kilojoules per mole. Again, very, very important. So that's amazing that how God has made these molecules. It's God or nature or whatever. So how precisely these bond energies are there, which makes us survive in this world. It's amazing. You see this 498 kilojoules per water. It's a methane, 435. And then you see here, HI, 298. Now, what happens in a peroxide? Hydrogen peroxide. Oxygen, oxygen, the lone pairs are close to each other. OH bond will be weaker, right? And that's the reason dimethyl peroxide, diphenyl peroxide, hydrogen peroxide will have lower bond dissociation energies. And when you have a diphenyl peroxide, the bond dissociation energy will be much lower. You can heat it at a very small temperature and get a peroxide radical. As simple as that, right? So this is what it is. You can see it now. CH3I 234. Oh, okay. This is the thing. So the bond dissociation energy has come up to 451. Hydrogen peroxide is at 213. And once you are putting some electron density with methyl or phenyl, it has come down. That's the idea basically. So you can break this oxygen-oxygen bond pretty quickly and make a methoxy radical or a OH radical right? A bromine radical, chlorine radical, like this. So from 500 kilojoules per mole, you have brought down by 1/3 or more than 1/3. So how a radical reaction is different to other common organic reactions or any other reaction? So this is what happens. For a chemist it is easy to understand, right? What's happening here? First reaction, what is happening? Alkoxide is a base. It has electron density over the oxygen. It is abstracting hydrogen. And forming a Br minus. So ROH, it is forming an alcohol. Here what happens? Alkoxide interacting with a methyl bromide, it's a nucleophilic substitution. Here one electron loss, it forms RO dot HBr, so it forms ROH. Here it forms ROH, here also it forms ROH, here it forms ROCH3, right? So these are the different things. You understand, right? So this is a proton abstraction, this is a nucleophilic substitution, this is a homolytic, it's a radical which is interacting and forming ROH and a formation of a Br minus, right? Or Br dot. Here it will form a Br dot, right? So let us see this product. So ROH, Br minus, proton removal. What type of a substitution reaction? It's a nucleophilic substitution reaction, bimolecular, and then hydrogen abstraction, right? Hydrogen abstraction, but through a radical formation. Now this is the way the homolysis of a bond happens, as I mentioned, right? With a very easy example of a peroxide bond. If you heat it or shine light, this will form. From one molecule you get 2 moles of OR dot, right? Very easily. So this is by cleavage of this bond. There is another way of getting a radical. If you have a ketone. In a ketone what happens? Carbon is electron deficient, right? Ketone is electron deficient carbon, del plus, because it is sp2, oxygen is pulling electron, right? So electron can come here, one electron comes, so it does a C dot O minus, right? So it's a radical. So these type of reactions we have already discussed, I am not going into it. This we discussed. You see this reaction, this is a very simple reaction to understand. Addition reaction, okay? Sodium also loses an electron because it is very favorable to oxidize. You know, right? Lithium, sodium, potassium can very easily lose its electron, right? So forming sodium plus ion and gives an electron. So these are the simple type of reactions which are possible. Then you have an elimination reaction. This reaction is very important. These are used as, this is AIBN, azo-isobutyronitril. This is used as a radical initiator. It initiates radical formation in organic synthesis. So this is very important for polymer industry. In a polymer industry, because you can make polymers utilizing radical chain. This radical is formed at a heating at 67 to 70 degrees centigrade, 72 degrees centigrade, you get this radical formed. Very easy to get these radicals, and it is driven by also entropy. This radical is also formed by entropic contribution. Why entropy contribution? Because nitrogen is forming gas, right? So this is an entropically driven radical reaction. Similarly, here as I discussed, diphenyl peroxide homolysis, you get this 2 molecules, and then you get a carbon dioxide, again entropically driven. You are producing a carbon dioxide gas, here you are producing a nitrogen gas, and these reactions are easy to do. So you can generate these radicals in your lab. Of course, what precautions you have to take? Precautions you have to take is, you cannot have moisture. If you have moisture, this radical will quench into the alcohol form, right? That's the reason, right? So you have to have very dry condition. then you can get these type of radicals in your lab. You can generate these radicals in your lab quickly. Okay, so what happens with a molecular orbital picture? Nothing to worry, right? I also used to get very worried on molecular orbital picture during my class, means BSc days. So nothing to worry. This is one of the simplest picture of molecular orbitals with a example with a methyl radical. So you can see doubly occupied sigma CH orbitals, right? There are 3 carbon hydrogen bonds, right? So 3 carbon hydrogen bonds means 6 electrons. So we have put 6 electrons, 1, 2, 3, 4, 5, 6, and there is an extra electron on the carbon. 7 electron system, because you have homolytically cleaved from methane. From methane you have homolytically cleaved, you have methyl radical and a hydrogen radical. So it's a 7 electron species. So this orbital is called, anyone? This orbital is called, what we will call this orbital? All 3 in same energy. So degenerate, of course, and this will be called as HOMO, highest occupied molecular orbital, because this is the HOMO. And then this is another orbital where your single electron is there. This we will call as SOMO, singly occupied molecular orbital. These are all paired. HOMO is stabilized, SOMO is at a higher energy. The unpaired electron is at a higher energy, and that's the reason these molecules are reactive. Why these molecules are reactive? Because the unpaired electron is sitting at a higher energy. And then there are equal amount of non-bonding electrons, right? And these are the antibonding orbitals, CH orbitals, antibonding. That's a molecular orbital picture. When you combine through a LCAO approach, linear combination of atomic orbitals, we make bonding as well as same number of antibonding orbitals, right? So this is a very simple picture. It shows that your unpaired electron is coming at a higher energy, right? And your paired electrons are stabilized. Once this molecule takes another electron, the electron will come here, and then the molecule will get paired. So if one electron comes from hydrogen, H dot, then what happens? It forms methane, and it will form a stable molecule, right? By pairing up this orbital. So then that's right, you got it. So then there will be 4 orbitals here, and those will be the HOMO degenerate of the sigma H, right? 8 electrons. That's the way. It's very simple. Okay, so this you can easily imagine now. This statement, greater value means stronger bond. Delta G energy required to homolize the bond will be much higher. That's what is our summary. And delta G energy released in combining the radicals, right? If it is too much, then it will always quickly combine and it forms this. As simple as that. Okay. So now see the radical stability. Let us go quickly to the stability. So tertiary radicals are more stable than secondary, then primary, then methyl. There is a reason for it. Chemists know that what are the reason for this to be stabilized, right? There are 2 reasons for this to be stabilized compared to this radical. One reason is very easy. You can also imagine. One reason is that this carbon is surrounded by umbrella. It is surrounded by like an umbrella. When there is a rain, you take an umbrella. So this carbon dot is surrounded by 3 umbrella. Methyl, methyl, methyl. It is protecting your carbon. And that is a kinetic protection of radical. When you are sterically protecting a radical, it is a kinetic stabilization. The other part of a radical stabilization is the thermodynamic stabilization. Thermodynamic stabilization will happen if there is a bond related stabilization, and that is what chemists understand. Although this is a very big divergence with physicists, chemists have thought over the stabilization using hyperpolarizability. through a hyperconjugation, not hyperpolarization, but a hyperconjugation. And hyperconjugation is a abstract theory. It doesn't exist. You cannot prove hyperconjugation. And hyperconjugation is what? Is these three hydrogens will stabilize this radical. These three carbon-hydrogen bonds will stabilize this radical. These three carbon-hydrogen bonds will stabilize this radical. So there are 9 carbon-hydrogen hyperconjugations possible which will stabilize, apart from the umbrella effect, the kinetic stabilization. Similarly here, there is not possibility. There is no kinetic stabilization. It's just a bare methyl radical. That's the reason it is very, very reactive. Here there are 3 hydrogens for hyperconjugation, and you are not having that kinetic protection. There is no kinetic protection here. So that's the reason this is more stable. And you see it here. Now what you understand? Once you have this, methyl, this bond is 439. So it is not so prone to form this radical. In our last slide we discussed. But this carbon-hydrogen bond, you see, has reduced by 42 kilojoules per mole. So it has a much more tendency to form the radical because it is getting stabilized. We look for better jobs, we look for better partners, we look for better, right, everything in life. Why? Because we want to get stabilized under that condition. And that is what molecule is doing. This has a more tendency to get this, and this is 397. And that's what exactly was the last slide. Right? You got it? So it's a very clear picture of a molecule which is where the paired electrons are paired to molecule which is where the electron has lost. The one electron has lost, or 2 electrons have got lost. Okay. So radical stability, I am not going into this. These you can imagine similar things, right? It is more of organic stuff. This is one picture of a radical. You don't need to understand it. It's a little complicated for a bit of physicists and biologists. I am not going into it. I directly go into my, so these I am not going into the radical things, I am not going into it. This I am going, so this is this I will be showing you some application of radicals. Do you know about tetrahydrofuran? Many of you have known tetrahydrofuran, right? We use in our labs, right? Physicists may not know, but tetrahydrofuran is a very common solvent in research laboratory. Tetrahydrofuran, if you have to do some very important reaction where there should not be any moisture, you have to dry it. How do we dry tetrahydrofuran? We put sodium. If we put sodium, sodium will capture the moisture. But then there is no way that my THF is getting dried. We cannot understand it. To understand that whether my sodium is good quality and sodium has taken up the moisture, what we do is we add benzophenone. And there is a very beautiful chemistry what happens because of radical. It gives a color. Once there is no moisture, the moisture is gone, the THF in presence of benzophenone and good quality sodium, it forms a absolutely deep bluish color like your chair. That type of color is formed. Absolutely dark Prussian blue color. Why it is doing? It's doing off because of this radical reaction. The benzophenone, we already discussed about the ketone taking an electron. Benzophenone is 2-phenyl with a carbonyl, right? Carbonyl group are acceptors, sp2 hybridized, phenyl is pulling electron. So there is much more del plus on the carbon, right? Sodium has a much suitably placed HOMO, you can say, to give electron. Oxidation potential of sodium is very good to give an electron to the benzophenone, right? So it forms pH C dot O minus pH, right? And that forms a blue colored radical. And this is what happens. Benzophenone in sodium, THF, it forms that. Now, what happens if there is moisture, if there is water? This will immediately form the OH. If there is water, it will immediately form the OH and CH, right? So that blue color will not form, right? So highly delocalized hindered purple ketyl radical anion is forming, which gives you this blue colored solution, and you know that okay, my THF, all water is gone. Sodium has taken up the moisture and it is absolutely dry. Now the question comes, why it is a blue color? Why it is a deep blue color? Right, why? That's the beauty of radical. Radicals are generally, whenever you have these type of organic radicals, right, organic radicals with aromatic rings and all, these becomes highly colored. Reason is very simple. You have seen the molecular orbital picture. What happens? The SOMO, which we discussed, singly occupied molecular orbital, and the unpaired orbital, the antibonding orbital, the SOMO and the LUMO, in these type of radicals are the gap is very small. It's very small. And that's the reason the electronic transition becomes very easy from the SOMO to the LUMO. And if the electronic transition energy is low, right, the absorption of the radical will happen at a lower energy. Blue means it's around 600 something nanometer, 580 nanometers, 600 nanometers, right? Something around that. So that's the reason. So SOMO-LUMO transition becomes easier, and that's the reason most of the organic aromatic radicals are colored in nature, beautiful colored. It is, yeah, of course. As soon as you open up, there is moisture, it will again go back, because it will capture the hydrogen from the moisture. But you are using the transient stability or certain lifetime of the radical to check it out. Okay, so this is one of the easiest example in lab which we use, radical chemistry. Okay, so this is how it is done. I am not saying. Yeah, that's a very important question, Pratima, what you said. Is when we say radical lifetime, if it is there to capture with our eyes, if it is there for 5 minutes, 10 minutes, 1 day, we call it as persistent. It is persisting for some time. If it is absolutely stable under ambient, it's a very, very stable under ambient condition. Very few radicals are there ambient. You can keep it on the bench. So this is a persistent radical. It has some lifetime to see it. Some others we cannot say it. It's a transient. Only spectroscopy, ultra-fast spectroscopy can do it at picosecond level or femtosecond level. Okay, so this is the reason, as I discussed. This is the reason that why you see color. This is the reason. This is HOMO-LUMO S0, S1 transition, singlet-singlet transition. In a dimagnetic molecule, electrons are paired. One electron has come. This electron has come from where? Has come from sodium. That electron has come from sodium. And now you have SOMO to LUMO, LUMO plus 1, LUMO plus 2. And these are called doublet-doublet transitions. This is singlet-singlet transition. This is a doublet-doublet transition. Why? Because you have a S equals to half. Right? So multiplicity becomes doublet. So this is a doublet-doublet transition. This is the difference between a dimagnetic molecule and a paramagnetic molecule. And that's the reason in aromatic radicals we see color. Color means the color which is visible by our eyes, in the visible region. Our eyes can see only in the visible region. Okay. This is a paper which had come in 1958 in Nature. This is another example of application. 1958 application of finding out the quantity of antioxidant in blood serum through a radical. Which radical? This radical I mentioned briefly in this slide in the very beginning. This is called the diphenyl picaryl hydrazide radical. So this what happens? This is the antioxidant. As you know, antioxidants have lot of OH bonds. Antioxidants have lot of OH bonds, right? Green tea, red grape, green grapes, right? Everything has these OH bonds, right? Quercetin and all biologists know, right? So this is the hydrogen coming from the antioxidants, OH basically. And the antioxidant, once you have reacted with a radical, and this DPPH is violet in color. DPPH radical is violet in color. You can ask me, why sir violet in color? Reason is again same, because of the doublet transitions, SOMO-LUMO transitions, violet color, right? Lot of SOMO-LUMO plus 1, LUMO plus 2 transitions, you get a violet color. Once you are reacting with different antioxidants, immediately it turns into yellow. So you have a clear naked eye visualization of antioxidants in blood. This is a Nature paper in 1958. Although this radical is not very stable, if you are keeping, you have to be very careful. In a sealed tube you have to keep it, to keep this, and this is very expensive. It's available in lab, in Mark and all. We also make this in our lab. So this is the paper. You please read this paper. This is a very highly cited paper, 21,000 2024, right? 1958, 1199. Please read this paper. This is a beautiful paper. Anyone can very quickly understand this paper. And this is the radical which has formed. So the antioxidant has formed the radical, and that's what we saw in our first example of the vitamin E. In the vitamin E first example, we also saw that. Yeah, absolutely. It's a very universal compound. But the problem is that its stability is not that what is claimed in this paper.
So only the color changes can be visualized.
Color change can be visualized, but while you are doing the reaction, then also the DPPH is also degrading itself if you are not taking precautions. That's a problem. Okay. But anyways. So this is, if you are a chemist, you can take a picture of it, or you can take a picture. This is what is the exact reaction. This is not discussed in the manuscript here, but this is a well-known methodology by which very well understood now. This is the reaction, what it happens. So this is camphorol, another antioxidant, very well known, camphorol, right? Used in many drugs and all that, right? So this is what the reaction happens. This is the hydrogen coming from the antioxidant, right? So this hydrogen is then forming O dot or O dot here, this or this, it forms a quinone, and then this is what it forms. This is the mechanism. So there are multiple other examples of this. Now we also did this, and this was the first work which we did in our lab in the very beginning when I had joined, and this was an accidental understanding. This molecule we were synthesizing for making an organic semiconductor. Okay, we wanted to make an organic semiconductor of this molecule, and for treating it to make on a wafer, right, we had to treat that with some amine and all that stuff, right? And my student said, sir, this molecule is colorless, pale yellow, very pale yellowish, like our wall color. And my student said, sir, my molecule is now turning brownish, dark brown, or like red wine. I said, why? Let us check the absorption spectrometer. I didn't have an absorption spectrometer, so I went to another lab, we checked it out, and then we saw beautiful absorption peaks. Those absorption peaks never come with a dimagnetic molecule. So sharp, very nice, goes up to the near IR. And then we check the literature, and it is a characteristic of the doublet transitions. Because there are SOMO, LUMO plus 1, LUMO plus n levels, right? Many, right? Doublet, D0, Dn transitions. And that means the amine are electron rich. Amines are giving electron, and amines, as you can know, histidine and all, right? All our allergy in the skin are because of these amines. If you go to the fish market, any one of you, if you are Bengali, if you go to the fish market, Arijit knows, if the fish are smelling badly, is because the fish is getting degraded. It's producing different types of bad amines. And those, that means you can actually check the freshness of meat, fish and all based on those amine formation, right? The freshness of it. So this, that means gives a understanding. From in the other one it was a antioxidant. Here you can actually check different types of amines. So what happens? We found out that these different amines are giving electron kinetically. Some electrons are given very fast, some electrons are given by the amines very slow. So that means from yellow to the red wine color is forming very differently with time based on the amine. Okay, so this is, it is getting heated up. Beta, it's getting heated up. It is looking black to you. These are the molecules. You see 6, 7. These are bulky amines. Amines are bulky. So it is not being able to give an electron. Because once the amines are bulky, the electron transition becomes slower. And that's the reason it has changed to little bit of orangish or something, but it has not completely changed into red wine color. Some of the amines have given color very fast, and some of it have not, like 18, 19. Tertiary amines have not been able to do it. Tertiary amines, pyridine, have not been able to do it. So that means you can selectively check out which amine, and if you do a kinetic profile, you can check it out. So now let us see the absorption spectrum. It's beautiful. I'll show you a real time absorption spectrum. So you see this. This is for NDI, this one. Now once you have added a small drop, this is what is happening. You check it out. So this was the NDI. This is coming down. This is coming down, right? This species is coming down. New radical is forming, and this has come down. New radical. That time I didn't have a spectrophotometer which goes beyond 1100. This was the departmental one which goes up to this much. So I can't see. I could not have seen it. So this is what it happens. So what you get? Multi-channel. This is UV. Then you have this visible to near IR. So you get a multi-channel probe, right? In the UV, multiple channels in the visible. So these are all the doublet transitions. This is the pi star transition of this one. The pi star transition is coming down, and these are coming up. This is the richness of a radical. You get lot of information, right?
How this absorption spectrum tells which one is doublet?
So this is your radical species, no? This part. As you remember, so you see again what's happening. This is the pi star of this molecule. Now you have started adding the amine. So this is what is coming up, no? This is coming up, this is coming down. So this is the pi star. And these are the doublet transitions, this part. Which is coming up is the doublet transition, which is coming down is the pi star. So this is for this species, this part. Clear? So this is, now you can plot different wavelengths, right? You have different multi-channel wavelengths which are possible to do it. Just another 5 minutes. Okay, I'll just complete it within 5 minutes. This is a very nice work of one of my student. This is a planar radical. I gave you a story of umbrella effect, right? You remember the umbrella effect? These methyls are protecting, 3 methyls protecting a carbon dot, right? Here this is a planar molecule, okay? And this, we can stabilize this planar molecule on the bench, this radical. How we are doing it? We have put 4 cyano groups, and this is making the molecule so electron deficient that it can take up electron very easily. Takes up electron very easily. It sucks up electron from anywhere, and the formation becomes very easy. So this was proposed by Professor Stephen Mattheil in 2009 and 10 in a concept note that this molecule cannot be synthesized. He had calculated through DFT and all that this molecule cannot be synthesized because there will be an explosion if you synthesize this, because this molecule is so electron deficient. As you know, trinitrotoluene and all are electron deficient molecules, they are explosives. So he had predicted that this molecule will explode. So then he had, in Nature Chemistry paper, he tried to synthesize, but he could not succeed. He had made some dicyano and others, but then the LUMO of this molecule is minus 5.2 in the calculated one. So then we thought of, and in Orglet 2012, a group from Singapore, Chuan In Chi, actually synthesized this molecule but could not isolate. So she could take the mass spectrometry, she could get it but could not isolate that molecule. So then we are just following up this work, and then we had in our mind that can we make it? Can we take up that challenge? And Yogendra was a fantastic student of mine. So we discussed, and then as I already told you that this molecule is so electron deficient, it can take up electron from anything, and iodide took an electron very easily from phosphonium iodide, and this formed a very stable radical. So stable radical that we can chromatograph this radical, and this is how we could ultimately isolate the precursor as well as the radical system. So this is the single crystal of the precursor, and this is the radical anion, and this is the phosphonium salt. Very long crystals we can grow. So this is the radical crystal, and this is the crystal of the tetracyano, okay, the precursor. And this is the beautiful part of radical. Again, I am saying this is the one which I really like of radicals, the color, right? This is the precursor. This is the one, the precursor, right? The black one is the precursor. But once you add an electron, the electron is coming from where? In THF, benzophenone, sodium, the electron comes from sodium. Here the electron is coming from iodide. Iodide is forming iodine. Iodide is losing an electron forming iodine, and the electron has come over this molecule to form this panchromism, and this is the beautiful part of the doublet transitions of the radical. Okay. Using this concept of pulling up electrons and making it so low LUMO molecule so that it can take up very easily electron and then stabilizing, we made these type of elongated molecules, right? These are very well known molecules also for lot of optical processes and semiconductors, and we can again get a single crystal of this radical anion. Here you again see what happens. The absorption spectrum goes up to 1250, 1240 nanometers. So the doublet transitions, because now you have made it more conjugated, right? As I told you, you make more conjugated, you get more red-shifted doublet transitions, right? So this is how we could make these molecule is again very stable. You can keep it on bench, radical. We did a radical long back, and a green you can keep it on the bench like this on a beaker, just like that. You can keep this radical. This utilizes a beautiful concept of inorganic chemistry, hypervalency, right? Phosphorus can expand its octet, right? So it can, once you add an electron, this electron will flow from this part and stabilize this through a n sigma star bonding. So this is possible. This is also chromatographically stable. Green is the radical. This is on a put on a chromatograph, and this is the yellow is this compound. So you can purify by chromatography this radical. Okay, and this is the orbital overlap. Why I said that this phosphorus can now form a bond with the oxygen, and this is the way that we can stabilize. This is the additional stability which we can get. Okay, now we can also utilize, so these are again the spectrum of the radicals, right? Beautiful titrations we can do it, as well as we can see You can say, sir, how are the other ways to check radical, right? Single crystal. You see the single crystal. Can you tell me what is happening? Because the effect of the one electron in the single crystal. So these are the single crystal data. Once one electron has come, this is the precursor. You have added one electron. So the carbonyl bond, once you have added one electron, the carbonyl bond will elongate. It will elongate, and that's what it happens. This is the carbonyl bond. This one, these ones. So you see 1.217, 1.211, it increases to 1.233, 1.225. Clear-cut understanding of a electron in a molecule. What happens also? This phosphorus oxygen bond, when you add an electron, this becomes shorter, non-covalent, and that is what is happening. 2.776, 2.719, non-covalent bond between this phosphorus oxygen, this phosphorus oxygen. So we proved it through a hypervalency. This is possible. Very simple concept of inorganic chemistry utilized in an organic molecule. We utilize this. So this reaction involved benzonitrile, which is very toxic. So we wanted that can we do it because this radical is so interesting, can we do it under green conditions? And we found out a way that we can actually grind all the components together mechanically without any solvent and can produce this radical. And this is the first example where we can produce this radical without any solvent, just by mechanical stirring. So this is the thing, green synthesis of radical anions. So this is absolutely possible, solvent free. You mix phosphine is white colored, this is yellowish color. We mix after 5 minutes, this green color start formation. This is the radical. Okay, and this we published in Green Chemistry. This paper is now very highly cited. Very easy to make. You can just grind components and make a radical. And there is no problem because radical is stable on the bench. You can make it on bench. Ball milling, full formation of the radical. Here it is a mixture of this product. Also, there is a mixture. It's not fully formed. After 30 minutes. So after 30 minutes, my student's hand has started paining. Right? But with ball milling, we can do it quickly, not quickly, 3 hours with a 21 hertz frequency. And this ball milling was done with Prasenjit Mal in Mysore. And up to 65% by ball milling. And 23 radicals we made, all bench stable, just by mixing this type radicals we made. 24 radicals we made. So multi-gram scale radical synthesis by sustainable greener route is possible. That's it. So I am sure I have been able to convince that radical chemistry is not difficult. Radical chemistry is useful. I could not go into the more physics of it, conductivity, superconductivity, magnetism. Please check it out. Conductivity, superconductivity, like metal-like conductivity, superconductivity, magnetism, ferromagnetism, antiferromagnetism, all are possible with these radicals because you can align the spin. If you are being able to align the organic radicals like this spin, you get a ferromagnet, right? If you are being able to align like this, it will be antiferromagnet. So these have really wide applications, absolute wide applications. So I believe in a short period of time, I hope I have been able to convince you that radical is not very difficult to understand, but it is easy to understand and can have lot of applications. Thank you so much. And direct mass spectrometry, because these are pure compounds, and EPR, absorption spectroscopy, because these will give absorption, because you will get a doublet transitions, no? Clear doublet, right? These transitions I will get. If it is not formed, no? If the radical is formed, I will get this. This is like absolute signature band if the radical is forming. Yellow is my precursor.
This is before reaction?
Before the addition of electron. After you add an electron from any source, this green color forms. Then we got it.
So you mentioned that the molecules are very transient, like
The initial part, methyl radical and all. But these are stable. These ones, the latter part.
the ones that crystals are formed.
Those are stable, very stable. Very stable. You can keep it on the bench.
They have this radical properties like in the crystal form.
Yes, absolutely. But at this point we have not been able to make a ferromagnet. We have not been able to. All of our radicals are mostly paramagnet. Now, if we can design a radical where our spin will get aligned like this under a magnetic field, then it will be a good thing for us. That will be our next thing. And if we can make a metal-like conductivity without these radicals, these are all possible. Let us see. I hope in the future we'll get some good results out of these radicals.
Sir, can we use this the radical formation for detection of some compounds?
Yes.
Like in
Yes.
like I work in here. So some compounds like pHs, cyclic aromatic.
Absolutely. That's what I showed you. That's why I showed you about the antioxidant. You took the picture of that paper, nature paper. That's what. You are saying polyaromatic hydrocarbons.
Yes, sir.
Polyaromatic hydrocarbons, you have to be careful with polyaromatic hydrocarbons, because some of the polyaromatic hydrocarbons in presence of light, they form a radical. So you have to be careful where what type of polyaromatic hydrocarbons you are taking. You should know about the property of it. Of course, these can detect. These radicals will detect.
There is a picture because I am talking about the atmosphere. So in atmosphere there is a mixture and concentration is very low. So sometimes whenever we are following some analytical method for extraction and then analysis on GCMS or
Yeah, so then in that case what you have to do is first you take a GCMS of that crude mixture, right? You know that sample, that these are the polyaromatic hydrocarbons, mixture of polyaromatic hydrocarbons which are coming from the environment. These are there. And that sample then you treat with any of the radical like DPPH or our radical or something, and then you take that sample for GCMS again. Then you see that which peaks have vanished or some different mass has formed because of the reaction of the radical.
we have standards for it. So I can do this experiment with standards, analytical standards.
Yeah.
And if they, as you said, if they are forming some radical and it is easy to detect.
So you have to be careful that your radical has to be stable. The radical which you are using during the experiment time has to be persistent enough to do the spectroscopy, and you should have a very clear picture of your sample. That's it.
How can we set and these hydroaromatic compounds, like so the particular hydrogen analyzed, like similar we want to
Detect.
for some
Detection. You can check the different polyaromatic hydrocarbons and see their basically again then you have to find out the dissociation energy, right, or the oxidation potential. Polyaromatic hydrocarbons are electron rich, right, so it will have a tendency to give an electron. So you have to first understand what is the nature of your molecule which you are trying to detect. Antioxidants are electron rich as well as OH rich, electron rich as well as hydrogen rich. So that antioxidant is giving H dot. And in polyaromatic hydrocarbon also it is a possibility that if the HOMO is very high of the polyaromatic hydrocarbon, then it can give an electron to the radical or the acceptor. It gives an electron, this becomes reduced, your polyaromatic hydrocarbon becomes oxidized. So what it happens, your polyaromatic hydrocarbon becomes a radical cation, and this becomes also a radical anion. These forms. This is one option. Other option is you do the first type of reaction where the polyaromatic hydrocarbon, there is some bond where the bond is weak, CH bond is weak. So it is dissociating H dot, and that is forming a radical, and that H dot is coming to your precursor like DPPH dot or something, and it is forming. So these are the two options you have. Either one electron or a bond dissociation.
We are getting changing the color, but they react with the atmosphere.
So that's a problem.
Yeah.
So then you have to do it on a.
They come in the same state.
Then you have to cut off the atmosphere
Like
in a desiccator, glove box,
yeah, humidity effect,
humidity.
pH effect.
Yeah. That's it.
Sir, how much time to take that from transition to stable?
From transient to stable.
That the radical can be how long we can stable. So you keep it 1 day after that it will.
So it depends. It depends. Some of the radical, the initial one, that methyl radical, transient. You cannot see it here. Transient. But the radical which I showed you later on, or the DPPH is persistent. You can keep it for some time, 1 day, 1.5 days, but it will degrade gradually. Some of the radical which I showed in our lab is stable. You can keep it on the bench. Maybe for 2 months, maybe for 3 months, maybe 4 months. You can just keep it. Depends on how you are designed.
The atmospheric oxygen can also.
Yes, again it depends on the orbital level. If your orbital levels can take up an electron from oxygen, depends on that. It's all the orbital or your bond dissociation bond energies basically. Any other questions? Physicist, आप थोड़ा सा इंट्रोडक्शन दे दीजिए हमें. I'll see. Start. Orijit I know very well from here. You tell you're doing research also.
I'm an assistant professor in School of Life Science, JNU. So
Oh yeah.
my background is now research area is infectious disease, particularly I work on tuberculosis, mainly post-pathogen interaction, understanding the disease pathogenesis. Mostly I will use mouse model I have been using in my previous research experience. So here also I will establish this mouse model and studying this mouse model.
Nice.
I'm Dr. Sashwat Chauhan. I'm an assistant professor in the Department of Biotechnology, Government University. My area of research is antimicrobial resistance, mostly antimicrobials. I study antimicrobial resistance, Pseudomonas aeruginosa, and Klebsiella pneumoniae.
Very nice. So with whom you are doing here research?
Here I am working with Professor Rajesh Mishra, School of Biotechnology.
School of Biotechnology. Rajesh Mishra.
And from Department of Environmental Science, Tezpur University.
Tezpur.
Yes. My research work is currently with air pollution and water pollution.
You are working here with ACS.
Sir, I'm Dr. Ajay Kumar, Assistant Professor in Government Science and Technology at the University of Bangalore. I also work in education. Basically, my focus more focused in aerobiology and organic characterization of the pollutants.
Pollutants. So what are the facilities you have there for characterization?
Sir, in lab I have this and all scientific devices for characterization of organic aerosols or mass. We have gas chromatography, mass spectrometry in central facility, as well as UPLC and LCMS as well. But I mostly do GCMS.
Pratima, I know very well. Yeah, exactly. She is very well known for sensors. Oh. So, VASP or okay. These are all analytical calculations. Analytical calculation.
Yes, analytical as well as simulations.
Simulations. Yes.
Dr. Santosh Kumar Desai, Organization Solution Department and Research Department. My specialization documents and stabilized structure, particularly oxygen and calculation.
Stabilization.
Stabilized structure.
Geochemistry. Oh. Nice. So you are in the department of
Environmental science.
environmental.
Sir, I am Dr. Kalapati, Dipsal University, Association of Plant Pharmaceutics. My areas are nanoparticles, formulation, drug delivery.
Drug deliveries.
I am
Nice.
working in Pratham.
Pratima ma'am.
So I am marketing as assistant professor in Department of Pharmaceutical Science and Research. My research is learning the using pharmacology that are integrated in network pharmacology, molecular dynamics, and experimental.
Drug delivery and all.
Not drug delivery.
Huh?
Not drug delivery.
No drug delivery?
No.
You mentioned, no?
Drug repurposing.
Drug repurposing. But after repurposing, you are not delivering.
That we will do.
It's all delivery is so important. You have to take help from him.
Yeah.
Ah,
Yes.
great.
Yeah.
Nice. Achha. Achha, you have a medicinal chemistry department.
We are generally in the development of newer cycles.
Heterocycles. Achha. So you are a synthetic chemist. Oh, lovely. Oh, very nice.
So we are doing for cancer, for examples, and now for acid.
For
And MSL.
MSL. What is that? Fatty liver. Oh, very nice. With whom you are working here?
I have taken transfer of the outside.
Achha.
And for computation, I have taken the Dr. Rajesh and computation I have taken
Pradipta Bandhavadhan. On? Nice. Nice. So we have a very diverse. Physicists are less here. Very few.